also be existing. Force is acting. Surface tension is a force per unit length. But some work done will also be acting. So that work done per unit area, that is known as surface energy. Work done per unit area, this is known as surface energy. So surface energy is basically work done per unit area. SI unit will be joules because this is energy only. Now see, there's a small derivation. This derivation can come in your examination. Now here what will happen? See, it says that consider a soap film having length of the free surface as L. So let's say this here, this is a rectangular, these are rectangular tubes, and I have, if you dip it here, you will notice that till this point you will observe some soap film. Let's say length is L. Surface tension is the force that is acting is surface tension. Now force due to surface tension. See, force due to surface tension was force per unit length. Class, whenever we are referring to soap film, now please make it a point to remember, whenever you are referring to soap film means double the length. You will double the length for soap film. Please remember this point. This is a very, very important point. Students do not remember this point. They usually mess up this point. This is the one of the most important point, because if in your exam, any of your questions, soap film is written, you will not write it as single L only. It will become double. Please understand this point, remember this point, because soap film is there. If a normal different film is there, your answer will be completely halved or doubled. So wherever soap film is mentioned, double the length. Like surface tension was force per unit length. So here it will be force by 2L. So force will be surface tension into 2L. From here, force will be surface tension into 2L. Why 2L? 2L because here we are talking about the soap film. That's why 2L. All right, so this is external force. Now, external force on the soap film. External force that we have to find out, this will actually be the external force, S into 2L. Now see, due to the external force for this soap film, what will happen? Because this external force is acting, let's say this external force is acting here. So it will make the free end extend over here. Let's say this was X initially, but now there is some change. Finally, there is some change that is observed. Let's say this change is delta X. Delta X is the displacement that occurred. Force was external force. C class, what will be the work done? Force into displacement. So F external dot delta X, right? F external dot delta X, that will be it. So when you put in the value of work done, it will be force. Force is S into 2L. This is delta X. S into 2L into delta X. So increase in the area. The increase in the area will be, see here, how we will calculate the area. This is the length. This is the breadth. So if the rectangle is formed like this, delta X and L. So area will be L into delta X. And what did I say? Whenever you are considering it as the soap film will be double. So area will also be 2 into L into delta X. This was the area, no? L delta X. Area will become 2L. 2L into delta X. The way we had, why? Because length is double. We have taken length as doubled for soap film. That's the only reason. Understood? This is the only reason. So increase in area is 2L into delta X. Now see, work done when you write work done by the external, that is surface tension. See, work done by external. Look here, class. Look here. 2L delta X. This is 2L delta X. What is this quantity? This means this is area. So here also you will put, this will become surface tension into area. That is the formula of work done. surface tension into area. Did we not start from this? Surface tension is work done by area. So from here, you can directly say that work done will be surface tension into area. So this is just a formula that will be used. By chance, if the derivation is asked in your exam, you'll have to mention these steps. All right, so surface work done or energy will be surface tension into area. Surface tension is force per unit length, and it is force per unit twice the length for soap fill. Note it down. Those who have joined late, you also note it down while writing any point that you will not be able to understand, get it cleared. Because we'll practice 1 or 2 questions. Minimum 2 questions we'll practice, then we'll start with excess pressure. That's why I'm saying, note it down. Wherever you are not able to understand, ask me. No, S into A means surface tension into area. S is surface tension. And A is the area. Surface tension, A is the area. See, now let's practice one numerical on this. I hope all of you have written. See, this says that calculate work done in blowing a soap bubble from radius of 2 centimeters to 3 centimeters. Class, as soon as you get soap bubble, now you will double the area, double the length wherever it is required. Right? Soap bubble is given. So for soap, soap film, soap bubble, wherever soap is involved, we'll be doubling it. So surface tension is given. Area, if you can calculate, then you can easily calculate work done. See, work done is what? Work done is simply surface tension multiplied by area. So surface tension is given 30 dyne. Let us calculate increase in the area, delta A. See, for a sphere, let's say this radius is R2, this radius is R1. R2 is 3 centimeter, R1 is 2 centimeter. So 4 pi R1 square, this will 4 pi R2 square will be the area of the second bubble minus 4 pi R1 square. This becomes the area of the first bubble. So this is the total change in area. But what did I say? You have to double it at the end if it is a case of soap bubble. All right. So now see what will be delta area. If you multiply 4 pi, you take 4 pi common, that becomes 8 pi, and R2 square means 3 square, and from here R1 square is left, that becomes 2 square. Understood? See, 4 pi I have taken common. So 4 pi from here, 4 pi from here, that makes it 8 pi. And R2 square is 3 square, and R1 square is 2 square. Then delta A, this will become 8 pi, 9 minus 4. That will be 5 into 8 pi, that is 40 pi centimeter square. Now see, this is the change in area. The surface tension is 30 dyne per centimeter. So work done will be simply multiply it. So 40 pi into 30 dyne. So that becomes 1200 pi erg. If you want, you can convert it into joules. And if you want, you can multiply pi also. So it's 3600 something answer you'll get. Copy it down. Wherever you have not understood, anybody who has joined late, wherever you're having difficulty in this, ask me. One more question we'll do, then we'll move on to the next topic, excess pressure. Use 3.14. That will be easier. Not joules. This will be in erg. Magnitude is correct, Tarif? Good. Good answer. Correct. But the unit will be erg because we have not converted dyne or centimeters into the SI unit, Newton or meter. No, that's why it will be in erg only. If you want, you can multiply and convert it into joules. If everyone has noted down, let's start with the second question. Or note down the solution. Those who are still writing, quickly write it. Then we'll do one more numerical first. Here this question says that if a number of little droplets of water of surface tension sigma, number of small droplets of water are there. They are having their surface tension sigma and all have the same radius. All these tiny droplets, these have the same radius r. They combine, all of these coalesce and form a larger, bigger drop of radius capital R. So whatever energy is released is converted into kinetic energy and we have to find the velocity. See, if you find the work done in this case, you can equate it to kinetic energy using work energy theorem. And if you have kinetic energy, then using half mv square, you can get the velocity. So now again, our work is to find out the work done. And how do we find out the work done? We have calculated. But see class, main thing is that we do not know what is the bigger radius, what is smaller radius, right? This is just given that number of droplets are present like this. So it's better if we find the relation between the radius of the big drop. So what can we do? See, volume of both the drops will remain the same. So volume of all these droplets, number of droplets is not mentioned, no? If number of little droplets, make this into a number. Otherwise, it will become very confusing to form. If a number of little droplets of water, no, make this number as 27. of water? 27. Take it as 27. Then your answer will become easy. So 27 times the volume of each small drop. This is equal to the volume of the bigger one. Understood this point? See, all these small drops, they'll join. All these small drops, they'll join together and they'll form the bigger drop. So volume will be the same. So if you multiply this into 27, so you'll get the volume of the bigger drop, this bigger one. So here, this will be 27. Volume of smaller drop will be 4 by 3 pi r cube. This will become 4 by 3 pi capital R cube. 4 by 3 gets cancelled. This becomes small r is capital R by 3. This is capital R by 3, right? 3r will be equal to r by 3. This is the relation of the radius. Now let us find out the change in energy. Let's find out the change in energy. We have the relation between the radius now. See how to calculate the change in energy. Change in energy will be here. Soap is not mentioned, no? Soap bubble is not mentioned. Number of droplets of water. So water is given. Soap is not given. We will not double the area this time. If you have to find out change in energy, we will not double it. So it will be surface tension into change in area. That is 27 into 4 pi small r cube minus 4 pi capital R cube. This will be the surface tension. This is energy. Now just equate it with kinetic energy. S into 27, 4 by 3 by R cube minus 4 by 3. Make capital R as small 3r whole cube. This is total energy. Equate it with half mv square. Whatever velocity's value you get it from here, that will be the answer. Note down the question. Tell me what is the value of velocity that is coming for each of you. See, now the next topic is excess pressure. Excess pressure basically means the total net pressure difference that is there. See, if you, even if you take a glass of water, now what will happen? There will be pressure that will be exerted by the atmosphere on the glass. For example, look here. Let's say here is the glass. If you fill it completely with water, so some pressure the atmosphere will be exerting, some pressure the liquid will be exerting. So there should be a net pressure. There should be a net pressure. So pressure difference across a curved surface of liquid, that means basically the excess pressure. So if it's a plain meniscus, both the pressures are equal. This is a plain meniscus means a flat meniscus. So flat meniscus is this last, or you can say, let's say you must have seen test tubes. So in test tubes also, the uppermost layer's shape is known as meniscus, the uppermost layer. So plain meniscus means whatever the pressure the vapor is exerting, exact same pressure is exerted by liquid. And whatever pressure is exerted, and if both are equal, that means it will form a plain meniscus because it will balance each other. Then you have convex. In convex, what will happen? Liquid will be exerting more pressure. So if liquid exerts more pressure from this side, what will happen? It will make this rise up and in the form of convex. In the form of convex. So we'll call it as convex meniscus. And if outermost pressure becomes equal like this, if it gets exerted, so vapor, this pressure exerted by vapor will be more. Means atmosphere is exerting more pressure. That is what are the different types of menisci. Now see excess pressure that is exerted in a liquid bubble. Net outwards pressure is P. Understand what has been written. This is excess pressure. There is a pressure from outside. This is known as atmospheric pressure. And there is a pressure inside. So difference between these is known as excess pressure. That's what I've told you. Whatever difference or extra amount of pressure is left, that is called as excess pressure. So that will be P inside minus P ATM. Now see, what is atmospheric pressure? What is inside pressure? And net outwards pressure is P. This net outwards pressure is P that I have taken excess pressure. Let's say radius of this drop is capital R. So if radius is R, surface area will become 4 pi R square. You know pressure is P, area is 4 pi R square. Pressure and area you have, so you can easily calculate force. See, pressure is force by area. So force will be pressure multiplied by area. That means 4 into 4 pi R square. Understood? Force will be pressure into 4 pi R square. This is the force on drop. This is the force on the drop. This is the force exerted on the drop. But still we have not received the final pressure. Now see, let us do it in terms of work done. Let us calculate work done. See, work done will be what? If let's say this is increasing, expanding with some dr. Like this is the bubble, no? The bubble is expanding and displacement is dr. So work done will simply work done will be force into dr. Put in the values of force. You will get force as P into 4 pi R square dr. This is work done. Now you have to find out, this is in terms of displacement and force, right? Force into displacement. You got this. One more definition of work done we have studied, no? Surface tension. This is one equation. This is from force tension relationship and force displacement relationship. If you see, just now we have studied work done and surface tension and the relation between the two. So work done will be surface tension into change in the area. Now see what is coming using this dw here. This will be surface tension into 4 pi. R, see, total radius will now become R plus dr. No, here R plus dr will become the total radius. So 4 pi r plus dr whole square minus 4 pi r square. A plus b whole square identity we can use. Let's use that one. R square plus dr square plus 2r dr minus r square. R square gets cancelled. And see, this increment in the radius will be very small, almost equal to delta R. How much a pressure or how much a bubble will increase? dr very less only. So dr is almost equal, this is almost, this is 0. So we get dw as 4 pi s 2r dr. That is 8 pi s r dr. Now you can equate these equations. This is one equation, second equation, and one more equation we obtained on work done this first. Equate 1 and 2. If you equate 1 and 2, it will be 8 pi. This is S, not 8. 8 pi S R dr. This is P into 4 pi R square dr. dr will get cancelled. 1r will get cancelled. 4 into 2 pi will get cancelled. You will be left with pressure as 2s by r. 2 into this is surface tension, this is radius. This is what you had to calculate. If you are talking about a soap bubble, you will double it. Excess pressure for soap bubble will be 4s by r, double of it. So air bubble in water or a liquid drop has only one liquid surface in contact with air. In case bubbles or liquid drops, the pressure on the concave side of the liquid air surface is greater than that of convex side. And these are also just important points to remember. Here what is happening? If by chance atmospheric pressure is also getting exerted, then just add atmospheric pressure at the last. And suppose, let's say one more pressure is there. If the air bubble is inside a liquid column, so there will be a pressure exerted by liquid column also. So at the end, you will add H rho G, that is the gauge pressure. Then you have the numericals that we'll see. First, tell me, what are all the doubts in this? Is it clear by all of you? Excess pressure, did you understand?
It's misunderstood.
Okay, good. So note it down then. Wherever you are getting stuck, ask me. We'll do then the numericals. See, this question says the lower end of a capillary tube of diameter 2 millimeter. This is dipped 8 centimeter below the surface of water in a beaker. What is the pressure required in tube in order to blow a hemispherical bubble at its end in water? So this is a hemispherical bubble. I have drawn a complete sphere. Just assume it to be a hemisphere. If you blow in air, a bubble will start forming, so that we have to calculate. See this here, what all pressures will be there? One pressure will be atmospheric pressure, one pressure will be the excess pressure, and one pressure will be the atmospheric pressure also. So here we'll use, there is not a soap bubble, no? So we'll use 2S by R plus P naught plus H rho G. So total pressure will be 2 into surface tension is 7.3 into 10 to the power minus 3. Our radius, diameter is 2 millimeters, so radius will be 1 millimeter or 10 to the power minus 3 meter. Atmospheric pressure is 10 to the power 5 pascals. Height is 8 centimeters, 0.08 meter. Density of water, 1000 kg per meter cube. Acceleration due to gravity, 10. Solve it. Tell me what is the answer coming. Only Tarif is the one who tries and solves the answer. Others also tried, no? Whatever answer you're getting. Yes, yes. To cancel 10 to the power minus 3. Easily cancel this. Yes, around this is the answer. some power errors are there. Just check the 10 to the powers. Otherwise, it should come out to be 1. I'll write it down, the answer. Almost the values are right. Just check the powers, Tari. This much pascals will be the pressure when you'll solve this. See, this question says that 2 soap bubbles have radii in the ratio 2:3. So radii ratio is 2:3. It means R1 by R2 will be 2/3. Then it says you have to compare the excess pressure and you have to calculate the work done. See, excess pressure is very easy. How do we write X? And it is soap bubble. So we will write 4S by T1. P2 we'll write it as 4S by T2. Now when you take the ratios of P1 by P2, not T1, sorry, R1 here. This will become, radius should come in the denominator. So this will become R1, this will become R2. So P1 by P2, 4S by R1, 4S by R2. 4S gets cancelled, R2 by R1, that is 3/2. So P1 by P2 will be 3/2. Then work done in blowing these bubbles. See, work done, how we will calculate. You know work done is directly proportional to R square. So if work done is directly proportional to R square, this will be R1 square by R2 square. R1 square will R1 by R2 whole square, 2/3 whole square, 4/9. This is the answer. Note it down. This is the last topic. Capillarity is the last topic from your hydrostatics. So hydrostatics will be over. See, till now we didn't discuss about the velocity or acceleration or movement of the fluid. No. So in capillarity also, it will be static. What you after this, whatever topics we'll be doing, we'll be considering rest of the acceleration velocity of it. Now see, let us just complete angle of contact, then the rest of the part we'll complete in the next class. Angle of contact basically means this is the meniscus. What type of meniscus this is? This is called as concave upwards meniscus. All right, this is known as concave upwards meniscus. You can see a concavity is there. So this meniscus is concave. So how do we calculate angle? Angle of contact. Basically drop a tangent. How do you drop a tangent? If this is the curve, then the tangent is drawn like this. So same way, drop a tangent and see whatever angle it makes with the container. This theta. This is known as angle of contact. Like this. See, if you drop it here, this becomes theta, which is angle of contact for convex. This is the tangent for plane surface. Sorry. See here, the plane surface, this is the tangent for the plane surface. So for plane surface, it always makes an angle of 90 degree. This is a plane surface. So three types of angles you will get. Angle of contact will depend on three factors. One, the nature of liquid and the solid in contact, means whatever is the nature of the liquid present inside and the container. Then the medium that exists above the free surface of liquid. It means this is your container. This is the liquid. This medium, this free space. And it is inversely proportional to impurities. It means if you keep on adding impurities in the liquid, if you keep on adding the impurities in the liquid, the angle will keep on decreasing. This is what is meant by angle of contact. Like I'll tell you in detail. See, this is a concave meniscus. Here, look at the angle. This is how you will drop a tangent. This is the container. So this will be angle of contact. It will always be acute. Acute means less than 90 degree for a concave upwards meniscus. So here, one thing that you have to notice, adhesive forces are greater than coercive forces. Remember, we did adhesive and coercive forces. Adhesive forces are the forces that are between two different objects like water and glass. So here the force between water and glass will be more than water in water. So liquid will wet the walls of container. Angle of contact will be obtuse. See here, if you drop a tangent, see the angle is greater than 90 degree. This is obtuse angle of contact for convex upwards. Here adhesive will be less. Means totally empty will not happen. Mercury in glass. Cohesive forces. Mercury bond is so stronger than the mercury glass bond that mercury takes all the molecules away. And finally, you have the plane meniscus. Plane meniscus means a meniscus, a flat meniscus which you give. This is always equal to 90 degree. This will always be equal to 90 degree. Here, both the adhesive and cohesive forces are equal. Like water and silver. If you take a steel glass or silver glass and put water in it, you will notice that the meniscus is flat. Whereas if you take a test tube, you will notice in test tubes also like this curves are formed, which are known as meniscus. So note down this angle of contact. Separate questions are also asked on angle of contact. Then in the next class, we'll complete with capillarity. Capillarity will be using angle of contact too. Note down all the points quickly. Text me done once you have completed it. Text me done in the chat column. And whatever doubts you have, you can ask me in between. All those who have completed, you can leave. Now we'll continue.